All right, we're back again with a video on reading quiz number 16 about arc length and parametric integrals. Arc length is something that we looked at in the lab, and basically we're trying to find the length of a function over a particular interval. We know this by other names in some other contexts. For example, perimeter is what we would call it in with rectangles and squares, and we would use the particular term of circumference when we're dealing with circles. Here we're going to apply this concept to just about any function you could think of. So in finding the length of a function, we can also incorporate the idea of finding the distance traveled by some sort of object that's traveling along that function's path. And we'll also take a look at parametric integrals, which have to do with our FTC, which we studied earlier. So first of all, what is arc length? We use the term arc length to describe the length of a curve. And we can use this formula to do a variety of things, such as prove the formula for the circumference of the circle, just mentioned, or finding the length of some sort of a path that just goes all over the place. So the arc length of a parametric curve involves the following formula, which we'll prove in class. And that is the integral from a to b of the absolute value of v of t dt, or the integral from a to b of the square root of dy dt squared plus dx dt squared dt, and the dt should not be underneath the square root there. Basically what we're doing is we're integrating speed. And when we integrate speed, we get distance traveled, as we've already learned. Distance traveled is another way of looking at the arc length, because all arc length is how far a particular function has traveled in a certain time period. An alternate form can be derived when we deal with y as a function of x, and that is the integral from a to b of the square root of 1 plus dy dx squared dx, where a and b are the lower and upper limits of x. And the way that this is derived is if we go through and we divide everything by an extra dx. And when we do that, by an extra dx dt, excuse me. When we do that, we end up with the dx dt squared part canceled, and we end up with the dy dt squared part eliminating just a dy dx, and we'll see that in class. Similarly, if we were to divide by dy dt squared, then we would end up with this formula down at the bottom, the integral from c to d of the square root of 1 plus dx dy squared dy. And we'll be using all of these formulas over the course of the next couple of days. So here's an example. Find the length of the function y equals cosine of x with x going between 0 and 2 pi. Here we notice that we've been given a function in terms of x. So we use our second formula here, the integral from a to b of the square root of 1 plus dy dx squared dx, all under the square root, dy dx, is equal to negative sine of x. This is something that typically you'll have your calculator for, and when we plug this into our calculator, we get the integral from 0 to 2 pi of the square root of 1 plus negative sine of x squared dx, which is 7.640. And that tells us that the length of this curve on this particular interval is 7.64 units long. A second example with this arc length, we are asked to find the length of the parametric equation, x of t is equal to 3t plus 1, and y of t is equal to 9 minus 4t on the time interval 0 to 2. And this is certainly something that we would be able to solve without a calculator. And since we do have a parametric equation, we can scroll back to our very first formula for arc length, which involves dy dt squared and dx dt squared. And in this case, dx dt is 3 and dy dt is negative 4. Putting that all together, we end up with the square root of 5 squared, or just 5, which we integrate from 0 to 2, and that final answer is equal to 10. This is something that I definitely would expect you guys to be able to do without a calculator. Example 3, find the length of x is equal to cosine of y with y going between 0 and pi. That should be a y on there. In this case, the arc length is the integral from 0 to pi of the square root of 1 plus negative sine of y squared dy, especially if things are all in terms of y. And we end up with the answer of 3.820. Notice that this is the same as if we did the integral from negative 1 to 1 of the square root of 1 plus dy dx squared dx, and the way that we would get dy dx squared is we would note that y is equal to arc cosine of negative x. The derivative of arc cosine of negative x, arc cosine of x, is negative 1 over square root of 1 minus x squared, which we can then square. And we apply our formula and we get the exact same 3.820. The limits, -1 to 1, come from the fact that we're going between 0 and pi with our y values. Other things to know for parametric problems are speed. We already talked about that in a previous incarnation of this presentation. The speed is equal to square root of dx dt squared plus dy dt squared. Distance, or length, is the integral of speed. Acceleration vector is just the derivative of our velocity vector. Dy dx is dy dt over dx dt. If we want to find a position at time b, given your position at time a, we remember our FTC, and we would just do x of a plus the integral from a to b of x prime of t dt. A y position at time b, given our position at time a, is the very same thing, except we're dealing with our y function. So again, when we integrate our derivative over a particular interval, we're going to get our total accumulation of our distance traveled in a particular direction. And we need to make sure that we account for our initial conditions. A tangent line, again, or tangent path is vertical whenever dx dt is equal to 0, and dy dt is not 0, and it's the opposite for horizontal paths that are tangent. When the particle is farthest to the right, left, up, or down, that's an absolute max or minimum problem. We would test our dx dt if we're looking for right or left movement, and our dy dt if we want to find our maximum or minimum y movement, up or down. So I'll go through one example here so that you can see how we apply this. The velocity vector of a particle moving in the plane has components given by dx dt, or the derivative of x is sine of 9 of t. Dy dt, which is y prime of t, is 4t over 1 plus 3t squared. And our initial condition, which is very important here, at time 0, the position of the particle is 1, 4. Part A asks us to find the distance traveled by the particle on the time interval 0 to 3. Okay, so if you'll recall, distance is the integral of speed. In our case, we're going to integrate from 0 to 3. We are given our dy dt component, which is 4t over square root of 1 plus 3t squared. And we're given our dx dt component, which is sine of 9t. We're going to square both of those parts, put them under the square root, and use our calculator to integrate. We end up with 6.145. Your calculator is very helpful on these sort of problems. And most often on the AP exam, you'll see these sort of problems on the calculator active section. Slide 2, with the same conditions, it asks us to find the position of the particle at time t equal to 2. The x-coordinate of the position will be found by integrating from 0 to 2 of our derivative. That'll give us our total accumulated x change. And we need to add our initial condition. So basically, we want to do 1 plus the integral from 0 to 2 of sine of 9t, that's our x prime of t, dt. And when we do that, we end up with 1.038, so not very much movement in the x direction. Our y-coordinate is found out in the same way. We're going to take y of 0, and we're going to add to that the integral from 0 to 2 of y prime of t dt. Don't forget your initial conditions. They're very important here. In this case, our y initial condition is 4, and we're going to add the integral from 0 to 2 of our y prime of t, which is 4t over 1 plus 3t squared, square root, and we end up with 7.474. Thus, our position at time 2 is 1.038, comma 7.474. It's not very much different from the FTC problems that we've done before. We're just adding a new twist to this by incorporating 2 layers of velocity, essentially. Same problem. In this case, we want to find the speed of the particle at time 2. So what we need is we need our dx dt at time 2, which we get by plugging in 2, and we get sine of 18. We're plugging in our 2 into our x prime, which is sine of 9t. And our dy dt at time 2 is equal to 8 over root 13, which is acquired from plugging in 2 into our derivative. So we need to square both of these and take the square root after summing, and we end up with a speed of 2.342. Slide 4, is the particle moving to the left or to the right at time equal to 2? Explain your answer. Remember, left or right movement has to do with our rate of change of our x. So in our case, we need to find out whether dx dt is positive or negative. Sine of 9 times 2 is sine of 18. And as it turns out, when you plug that into your calculator, you end up with a number that is negative, in fact. your number is going to be negative 0.751. So all we do there is figure out whether our dx dt is positive or negative. In this case, it's negative, so the particle moves to the left.